Okay, so last time, this is what we were talking about. We found ourselves in this really disturbing situation where we had to recognize that even though every time you compose functions, you end up with a diagram like this, where you can kind of recognizably see how you're actually composing two actual functions, right? Not every diagram is necessarily a composition of functions, right? You see here, this one here just absolutely isn't. Now, this is not a pointless abstraction because, for example, this example down here, these equations that you're given that relate the given variables leads to this diagram, right? And so, for example, y1 is a function of x1 and x2. And let's see, y2 is a function of x1 and x2. And let's see, z1 is a function of x1, y1, and y2. And last one, let's see, z2 is a function of y1 and y2. Okay, so this actual diagram up here, you would naturally want to write down, having seen these equations, and yet this is not a composition of functions as written. We only have a chain rule for compositions of functions. We're dead in the water on this. We got nothing. Right? So that's the problem. That's where we left it last time, as I recall, and we're going to try to pick up from there and figure out how to make sense out of this. So the big idea is to introduce a new variable if necessary. And what I'm going to do is I'm going to basically put a new variable right here, kind of, if you will, halfway between the z1 and the x1. And let's see if I can, I'll tell you what, I'll have to zoom out a little. Oh, and I forgot to hit this button here. There we go. So putting that new variable right there kind of solves the problem for me. Now I've got x1 and x2 there, and I've got the new variable and y1 and y2 there, and I have z1 and z2 there, and everything looks good in this bottom diagram. This does look like a composition of two functions, right? There's the one that takes the green to the blue, and there's the one that takes the blue to the dark blue. Right? Now, in order for this to be fair, keep in mind, let me clean all this up. I'm losing track of my colors. Z1 is supposed to be a function of x1, y1, and y2. Now I've got Z1 being a function of the new variable and y1 and y2. So what gives? And I do need to make this legal. So I need for this new variable actually to be literally x1. Right, so this new variable that I kind of inserted in here, I'm calling it x1 star because it's x1. I just need to view it as being a separate variable, even though it's always got the same values. I need it to be a separate variable so my diagram makes sense, and so this actually is a composition of functions. So I claim by inserting this here, I haven't actually done anything. Right, by effectively getting rid of, let's see here, by getting rid of this equation and replacing it with this equation, z1 now being a function of x1 star, but x1 star being x1, it's still the same, nothing happened, it's all fine, except now my diagram makes sense. Everybody on board with that? Okay. So now, questions that I previously was kind of like, I don't know what to do with, like, what would it mean to take a partial of z1 with respect to x1? This was a catastrophic, meaningless garbage question initially, because partial with respect to x1, what am I supposed to hold y1 and y2 constant? But y1's a function of x1. That just doesn't make any sense, right? now becomes a perfectly reasonable question. Partial of z1, let's see here, do this in green. This was, I don't even know what to do with it, but now partial of z1 with respect to x1, well, there's z1, there's x1, no problem. Partial of z1 with respect to x1, I'm just going to hold x2 constant, and chain rule problem, no issue. Everybody happy? Okay. So then we just, a matter of sort of doing the details. There are three different paths. There's a first path by way of x1 star. There is a second path by way of y1. And there is a third path by way of y2. So I get a term for each one of those paths. Right? A nice little simplification happens along the way here, looking at, what is the partial of x1 star with respect to x1. Oh, well, that's asking for, what is that partial? Well, keep in mind x1 star is x1, so this is just that's just one. Right? We're taking the partial of something with respect to itself. So easy. And this gives us a meaningful answer to the question of what is this partial derivative? It's this expression there. Okay, so heads up on this kind of thing. I encountered the following many times in my past life as a college physics major, and you're going to encounter sets of equations like this that lead to diagrams like this that you can't work with as is, right? And all you have to do is fix it. Insert a little, create a new variable that turns a nonsensical circumstance into a normal circumstance. Everybody happy? Okay. All right. Okay, let's talk about second derivatives. Second derivatives. This is mostly kind of just a matter of doing it. There are two big lessons that you want to take away from this discussion. The first one is go slowly and carefully. Don't try to do too much in your head. Don't try to save pencil lead. Don't try to save paper. Right? Take your time. Each step should be a simple step. So slowly and carefully. The second thing is going to come up naturally in a minute. We'll see this again. I'll come back and talk about this again. But the big idea is if you have a function of x and y, then so are its partials. If z is a function of x and y, then zx, right? The partial of z with respect to x, also a function of x and y. Innocent observation. We'll see how that comes up in the discussion here. I'm not going to state this as a theorem. I think that would be more trouble and confusion than it's worth. I think the best way to get a good feel for how to do these kinds of things is just dive right in and do an example. What I'm about to show you is the classical first example that I think practically everyone sees as their first example because it's actually pretty geometrically meaningful and relates to a cool application I'm going to show you in a minute. But anyway, let's get it. That's foreshadowing. Okay, here we go. We are starting off with z being a nice function of x and y. And furthermore, r and theta are polar coordinates. Now, keep in mind what that means. If r and theta are polar coordinates, then x and y are functions of r and theta. That's how polar coordinates works. All right? Everybody with me? Y'all will recall from last time that I'm a big proponent of having a good diagram that represents, which variables are functions of what, and which variables are playing what roles in what circumstances, and what's an intermediate variable. The diagram will keep track of all of that for you. You just really have to have a good diagram to make sense out of all this stuff. So there it is. My question is to compute a second partial with respect to r. That's what we're going to try to figure out how to do here. Obviously, the first step is to take a first partial with respect to r. and this being z, that being r. There's two paths. That path gives you that term. This path gives you that term. That's just the chain rule, right? We did a bunch of these last time. And then there's a couple of simplifications. That's just notation. Remember, sometimes we like to write partial derivatives in sort of a kind of a Leibniz-like notation, and sometimes we like to write it with a little subscript, kind of Newtonian-like, right, indicating what variable we're taking the partial with respect to. Okay. Don't forget, r and theta being polar coordinates. I actually have explicit formulas for x and y. This y right here, it's literally polar coordinates. Y is r sine theta. So the partial with respect to r is just sine theta. Right? All right. Okay, so we've done the first step. We've computed the partial with respect to r. By the way, for the moment, don't look at this. We'll come to this in a minute. That's a distraction for the moment. Okay, yeah, so we have the partial with respect to r. That's the thing that I now need to take an r partial of to get what I'm actually interested in, the second partial. Right? So now I'm going to take the r partial of the r partial we just computed. All right. And again, slowly and carefully. Don't try to leap over too many steps in one step. First thing to observe about this. I'm taking a partial with respect to r. There's r. Partial derivative means that all of the other input variables are to be held constant. So r gets to be a variable, but all of the other variables over here in its world have to be held constant. So in particular, that means theta is to be held constant. Everything's a function of r and theta. Partial with respect to r means theta is held constant. Is everybody okay with that, right? Everybody remember? Partial derivatives, the other variables are constant. So here's the good news. If theta is constant, that means cosine theta is just a slightly uglier constant, but it's still a constant. And likewise, sine theta is a constant. And when you have constants, they just factor right on out in the usual way. Everybody cool with that? Excuse me. Likewise, the derivative of a sum is the sum of the derivative. So there's kind of a... Actually, by the way, this is sort of an example of the linearity of differentiation that we talked about last time, probably, or recently, certainly. Okay. And now's where we have to start really thinking carefully about where to go from here. We've got to figure out, what does this thing mean? Right? What do I mean by the partial with respect to r of zx? I'm going to start by telling you what it doesn't mean. It's a common misunderstanding, common mistake that I see on student papers all the time. And I'm going to show you where this landmine is so you can make sure not to step on it. Right? And a lot of students will look at this and think, how about I call this ZXR, right? After all, I'm taking the x partial and then I'm taking the r partial of that. Isn't this the notation that we use for that? And I claim that doesn't make any sense. That's just kind of nonsense. Because look, this suggests that z is a function of a collection of variables including both x and r. Now let's go to our diagram, which illuminates so many things. Z, this notation would suggest, is a function of all of these other variables. It's got to include both x and r. And that doesn't make any sense at all. For example, if this were the case, if z were a function of sort of simultaneously of all of these variables, for one thing, notice they're not independent, as they should be, right? And notice further, if this were what z is, how would I take an R partial of Z? Would I be allowing R to be a variable and then trying to hold all of the other input variables constant? That doesn't make any sense. If R is a variable and changing, X is going to be changing. But it's supposed to be a constant. How can it be both a function of a variable and also a constant? It doesn't make any sense. Does everybody see why this is nonsense? You just can't, it doesn't make any sense. Okay. So that's a landmine. Don't step on the landmine. Now let me show you the right way to think about it. Right way to think about it is to think carefully again about what this thing here is, Zx. And this was the statement that I made at the beginning up here. I made the observation that if Z is a function of X and Y, then its partials are also functions of X and Y. That means that the partial of Z called Zx is a function of X and Y. And if Zx is a function of X and Y, then let's say so on the diagram. And notice that's what I've got right here. Zx, function of X and Y. I'm putting it where it belongs. If you've got something that's a function of X and Y, then it goes here on your diagram, indicating that it's a function of X and Y. Right? And then likewise, Zy, that's going to come up in a few minutes. Zy, also a function of X and Y, so I add it to our diagram as well. So my diagram has grown to accommodate the new expressions, the new, I'm going to call them variables, because they are effectively the values of functions of other variables, and so I'm going to call them I could give them another name. I could call it W, but we don't need to. They're variables. They should be on our diagram. Everybody happy? Now, having done that, what's the partial of Zx with respect to R? Okay, well, there's R, and here's Zx. And this is a pretty easy observation. How do I take the partial derivative of Zx with respect to R? I'm just going to use the chain rule. And there are two paths. There's what you might call the X path. That gives you what you might call the X term, right, as we usually call it. And then likewise, if look at this, my stylus just died. I don't know why my stylus, I charged this thing at lunch. Oh gosh, I'm sorry. Let me plug it in real quick. Just a second. Okay. Plug it in.
Do you want a different one? We have another one.
That's okay. I think I could. I appreciate it. I think I could just use my finger here. Okay. So second path, intermediate variable y, and that gives me a y term in the chain. Okay, does that make sense to everybody? Let me walk through this whole thing again, just because there was an awkward interruption right in between. Looking for the partial of Zx with respect to R, I see where they are in the diagram. I have two paths, therefore two intermediate variables, and I get one term corresponding to each one of the intermediate variables. Is that cool? Really nothing that weird if you think about it. All I did, and I made this observation at the start of this example, slowly and carefully, right? And make sure to keep your diagram up to date. And when a new variable makes an appearance, like Zx made an appearance here, oh, well, yeah, put it on the diagram, and then let the diagram do your thinking about the chain rule for you. Okay, so now let's see here. I will now come over here and look at, we need to take the partial of Zy with respect to R. And again, I have two different paths. So this is going to be, it's going to turn into that by way of there being an x path and thus an x term and a y path and thus a y term. Same deal. Keeping the diagram up to date as I proceed and new stuff appears. Let the chain rule do my thinking for me. Yeah.
So I want to understand how there's a y path for zx because I thought we kept y constant while getting to zx.
Yeah, no, I hear where you're coming from. So let's talk about that, and we'll go back to the zx example per your question. So let's see here. There's zx, right? And you were right that while we were talking about zx, the way we compute zx is that we hold y constant. But very importantly, we hold y constant temporarily for the purposes of that computation. The result is that zx is a function of x and y, right? So after you've computed it, yeah, it's a function of x and y continue to be variables. Does that make sense?
It does, but I didn't understand how it's a function of both x and y. Maybe I can
Yeah, sure. I mean, just let me go back a few pages. Whoops! Oh, I hit the wrong button. Oh gosh! I don't know if y'all noticed this is a new app that I'm using, and it's a little different from my previous one. It's better, but it's also a little weird. Let's see here. Nope, I went too far. Still getting used to this new app. Yeah, here we go. Okay, here's an example. There's a function of x and y. Take a partial with respect to x. Right? For the purposes of doing this calculation here, we're going to treat y like a constant, but look what the result is, and it's clearly a function of x and y. Is that satisfying?
Yeah.
Okay. Yeah, cool. Did I see another hand? Yeah.
So let's say when you calculate zx for one function, all the y terms drop out.
Yeah, that's a irrelevant coincidence. What I would say then is so I can hear where you're coming from, but if you have a function of x and y, and if the y terms just kind of there aren't any left, then it's just a simpler function of x and y. It's still, boring though it may be, still a function of both x and y. Yeah, right. All right. Okay, so moving along. Yeah, okay, here we are. Okay, so we're practically done at this point. That is the tricky bit. The tricky bit is to keep your diagram up to date, add new variables as needed, slowly and carefully, and then when you find yourself looking at a partial, identify where are the relevant variables, look at the relevant paths, write down the corresponding terms. So again, that's kind of, that's the only twists to be on the lookout for. Now, I want to address the little final details. Notice this. We have an alternate notation for this already. Partial of zx with respect to x, there's no chain rule here. There's no intermediate variables. Z is directly a function of x. And so zx is directly a function of x and also y, of course. But anyway, so the point is this partial is just a straight up second partial, no issue, no problem. Likewise for various other factors here. And then notice as well, we have another polar coordinates simplification there. And likewise here and here and here. That's just polar coordinates. And so if you sort of adjust your notation and take the appropriate polar partials and kind of collect terms, move things around, and your answer ends up being this. Everybody happy? Okay. All right. Okay, why do we care about this? I'm going to give you an example that involves, this is a very important application. This thing here is called the Laplacian operator. It's huge in physics, which means it's huge in engineering, right? And it's awkward to work with sometimes because you notice you have to take a bunch of second partials, and partials are relatively easy to take, but nevertheless sometimes they can get a little tedious, and that is going to come up in what we're going to see in a minute. So I'm going to make the following observation, and that is that I can rewrite this rectangular Laplacian. Call it that because it involves partials with respect to rectangular coordinates. Can rewrite that as this spherical Laplacian. It's the same thing. It computes the same result, but you'll notice that the derivatives that we're taking in this spherical Laplacian are all partials with respect to spherical coordinates. Right? How do I know these things are equal? It's the result of a tremendous amount of tedious calculation that I am not going to impose upon you. I'm not even going to recommend it to you. It's more ugly than I think it's really quite worth. But I do want you to see, roughly speaking, how that calculation would go. And so, for example, let's look at just this little part right here of our alleged spherical Laplacian. Second partial with respect to theta. Well, here's f, and here's theta. Notice, just like on the previous page, if f is a function of rectangular coordinates, and if polar coordinates are what they are, right, then this is, computing this thing here is really just a matter of doing what we did on the previous page. It's a second partial, this time with respect to a spherical coordinate instead of a rectangular coordinate, instead of a polar coordinate, but it's second derivative chain rule. And you can totally, inconvenient though it is, you can totally compute that, and you can compute all these other various partials that there are. And like I say, it's a lot, and I'm not recommending that you do it. But you can use this chain rule map, as it were, and append as needed and follow the procedures and throw it all together, and what you'll find is that it adds up to the rectangular Laplacian. Okay, now why do we care about that, right? I mean, who needs it? Tempting to look at this expression here and say, okay, you know what, thanks but no thanks. Right? Pass, right? I'll just stick with the rectangular Laplacian. This looks a lot nicer. Let me try to change your mind on that. And let's see a real situation. This is a very real, meaningful, important calculation that comes up in the real world. Suppose you want to understand gravitational potentials, potential energy, right? Electric potential is actually very similar, mathematically, very similar quantity of voltage, right? So pretty big deal in understanding electrical engineering is to understand electric potentials. Right? Well, a function that describes an electric potential has to satisfy this equation. Now, why that is a physics thing that would cost us 20 minutes to talk through. That's not our problem. That's somebody else's problem, right? It'll become your problem when you take the appropriate physics class, right? But the punchline is electric potentials have to obey Laplace's equation. All right, so it's going to turn out that a very, very important solution to Laplace's equation is this function right here, which you can write in rectangular coordinates. A lot of people, again, like to cling to rectangular coordinates because it's familiar, right? None of this weirdo Greek letters nonsense, right? But eyebrows get raised when you see, look how much easier it is to write it in spherical coordinates, right? Looking kind of tempting. So how do we confirm that this does what I claim it does? Well, I mean, it's a brute force situation. We've got to take our Laplacian here, which again, you can either think of rectangularly or you can think of spherically, take your pick, choose wisely, right? You're going to have to then apply it to your f function here, which again you can write rectangularly or spherically, and you've got to actually chug it out, right? So you have to either take the rectangular Laplacian of the rectangular candidate, or you have to take the spherical Laplacian of the spherical candidate. Again, choose wisely. Right? Now, a lot of people will look at this and say, you know what, thanks but no thanks. I'm going to go ahead and do the rectangular one. And I think everyone should do that calculation once in their lives, at least once. You're going to do it in this course as a homework exercise. And I'm going to go out on a limb and anticipate that you're going to decide that you don't like this option. It turns out to be algebraically hairy, right? It's just got a lot of tedium in it. You can kind of see it coming. Like, take any one of these partials. Look what you have to take a partial of. It's a quotient. You're going to have to use the quotient rule. In the denominator, you have a composition. You're going to have to use the single variable chain rule. There's a square root. That's going to bring up fractions and fractional exponents. It just gets a little ugly, right? And don't forget, you got to take 6 of these ugly partials. It gets hairy. So that's option 1. Option 2, now again, at a glance it looks worse, but I claim it's not. This is actually really easy. In fact, this calculation here is so easy, we're going to do it right now without really having to write anything down. It's that easy. This is a snap. Here it goes. We will start by, let's see here. I'm going to start by applying this term to our candidate function. First part of that is to take a theta partial of that expression that has no thetas in it. That's 0. And so it doesn't really matter what I have to multiply it by. Just the mere fact of taking a theta partial of something with no thetas makes that, I'm going to get 0 for this entire term, right? So morally, this whole factor here disappears in a puff of smoke. Right? That's nice. It didn't happen in the rectangular calculation. The rectangular calculation was ugly. Right? Okay, next step. Let's look at this term here, the first step of which is to take a phi partial of this expression that has no phis in it. So again, 0. Again, this whole expression here disappears in a puff of smoke. And we are done with that. We just made most of the ugly expression disappear, and we haven't done any algebra yet. Everybody with me? Everybody's starting to. This is pretty nice, right? This is a pretty cool appeal there. Little bit of effort comes up in the last step here. Now we're going to be looking at this third term, well, first term, I guess. I need to take a rho partial. There is a rho in that expression. All right. Rho partial, k over rho. I get negative k over rho squared, which I'm going to multiply by rho squared, it says, right? And what happens when you multiply rho squared times constant divided by rho squared? And what you get is that this right here is a constant. And if that's a constant, then the partial of that constant is again 0. That third term disappears. We're done. The answer is 0. We didn't even have to do any algebra to speak of. Everybody good? So really, really nice, right? Picking the right coordinate system to do business with is tremendously important to keeping your sanity in working stuff out. And ultimately, why this works is because if you think about, let's say, gravitational potential, if you have a single point mass, right? If you think about it, it's natural that it be sort of spherically simple, if you will, right? Because distance is what controls potential energy. How far have you moved away from the center of where the mass is, right? So rho, being a spherical coordinate, makes it pretty natural to want to do business in spherical coordinates for this kind of a problem. And calculations analogous to this that involve all kinds of physics that where you have a centrally located thing and stuff sort of is controlled by distance from that centrally located thing. Spherical coordinates is what you want to do. Is everybody on board? Yeah, question.
If the Laplacian is equal to 0, does that have like a geometric or a physical kind of?
Yeah, no, that's a great question, and it's a 20-minute conversation about physics that it's not part of this course, and so I'm gonna label that as I did before as somebody else's problem. And look, it's cool stuff, and there are good reasons, and it does make sense ultimately, but it's not what Math219 is about. Yeah, right. But you'll see it when you take some future either physics class or engineering class, I'm sure. Okay. All right. Okay, so so summary. Why are we talking about this again? Important calculation uses this spherical Laplacian. This spherical Laplacian we can justify by talking about second derivatives in the chain rule as applied to the diagram representing the variables that we're talking about here, right? So this kind of calculation back here, second derivatives with the chain rule, is what makes all of this possible in the first place. Okay. All right. Okay, moving along here. Hopefully my stylus is recovered by now. Let's hope anyway. Let's see here. Yep, we're in business. Okay, directional derivatives. I want to start by talking about partial derivatives. We've seen a bunch of facts about partial derivatives. They're good for several different things. Here's sort of a running list now of what the partial derivatives are. It's a slope of the graph. It's a multiplicative factor. It's what you multiply by input changes to get output changes in certain circumstances. Here's one I haven't actually done yet, at least not in this algebraic form, but I claim you can view a partial derivative as being this expression right here, and I want to talk about this expression. Let's see here if I can. Why won't it let me pinch? There we go. Okay, let's talk about this expression right here. Look at what's inside here. We've got A at some location. And then plus t times a vector. Y'all will recognize this construction as being a parametric line, right? So this is a parametric line that describes my being at a certain point and moving with a velocity. Wait a second, this EI vector points in the direction of one of the coordinate axes. So this says I'm at the point A and moving in the direction of one of my variables. I'm moving in the xi direction. So what am I actually calculating then? If you think about it, what this is saying is if I'm at the point A and moving in the xi direction, I'm calculating how fast f is changing with respect to time. This is a fancy way of saying how fast does the function change as I move in the xi direction. That's what a partial derivative is. That's one of our primary interpretations of a partial derivative. So, so I'm going to say that's something we know about partials. And then similarly, this is something we know about partials. And easier argument to be made here, after all, the gradient is just made up of all the partials, right? And EI is made up of a bunch of zeros with a 1 in a certain position. So this dot product almost everything gets multiplied by 0, except I get 1 times the appropriate partial derivative, and the answer then is the appropriate partial derivative. All right, is that cool? Calculation y'all can flesh out if you'd like. Okay, so so a partial derivative has these 4 properties that I have in dark blue. All right, now let me say that a little bit differently. These four expressions or quantities that I have in dark blue here, these 4 things are all equal to each other. That's really the big takeaway that I want to start with in this argument. These 4 things are all equal to each other. Specifically, these things are all equal to each other if the direction that I'm talking about is the direction of a standard basis vector. So that's the direction in which you take the slope. It's the direction in which you have to be moving if you want to view it as a multiplicative factor. It's the direction here in this rate of change of f. It's the direction that you dot with the gradient there. Okay. So these 4 things all equal to each other if you're moving in that direction. Okay, now next observation I'm going to make. There's something arbitrary about coordinates and variables. Y'all remember from Math219 that if you have a basis, right, you can talk about coordinates with respect to a basis. It depends on what basis you pick. And if you have a basis picked, you can change to a different basis and you get different coordinates, but it's still going to be coordinates. They're just as good as those coordinates. They're just with respect to a different basis. Kind of who cares, right? And if you think about it, the function that we're interested in here, right? This function, we talk about it as being a function of several variables, but that is really, again, it's kind of an illusion. Functions are usually not functions of variables. They're usually functions of points. And let me talk about one of our classical examples to just kind of for relatability purposes. Let's talk about temperature in this room. I could set up a coordinate system and say, here's my axes, these are my standard basis vectors, and therefore each point has certain coordinates, and temperature, I can compute the temperature at a given, set of coordinates, but I don't really need that. The temperature at this location is already a thing, just being a location, right? How I choose to write that in coordinates is notation, really, more than anything else, right? So functions are functions of locations, ultimately, not coordinates. Coordinates are arbitrary and unnecessary. Okay, so that said, if the case has been made that these 4 things are equal to each other when you're talking about a particular unit vector defining the direction of one of your axes, well, if the axes are arbitrary anyway, then these 4 things should be equal to each other for any unit vector. Because, okay, let's suppose I have this coordinate system, right? These are my standard basis vectors, and now I want to talk about that direction. Okay, well then I made a weird, silly choice of my axes. Now let me just set up my axes like this. Now that direction is the direction of that I was talking about. Now that direction that didn't used to be is now a standard basis vector. Just write everything with respect to an appropriate choice of basis. So the pitch that I want to try to persuade you of is these 4 things are always equal to each other. We just only call them partial derivatives once we've picked an axis system and talk about unit vectors in those directions. Well, these 4 things are always equal, though. That's the pitch. So I'm going to write that down. These 4 things. So let's see, here they are. This and this, these two new expressions that I had written down above, and slope of the graph and multiplicative factor, these are equal for any unit vector. It does have to be a unit vector, but they're always equal to each other. Now, what am I going to call this? I can't call these partial derivatives. Partial derivatives, that's a term that we've already used to mean, given that we have a coordinate system set up, this vector is one of our standard basis vectors, and that's not what we're talking about here. So I can't use the term partial derivative. We just invented a new term. The term is directional derivative. Directional derivative is just basically a substitute for the idea that, I'm going to take a partial derivative in a direction that could have been just as well one of my coordinate directions. So directional derivative means effectively partial derivative, just in a different direction. Here's the notation that we use. We use a capital D. The vector describing which direction you're talking about is a subscript. Got to indicate which direction you're talking about. Obviously, you have to indicate what function you're taking a directional derivative of. You have to indicate what point you're taking that directional derivative at. Right? That's kind of familiar, hopefully. So there's our notation for directional derivative, and this notation, this terminology, directional derivative, you can interpret it as any of these four things. They're all the same. Yes.
Where did DS come from?
I haven't gotten to that yet.
Okay.
Yeah. So that's going to be one of the next things I want to talk about. Now, slope of the graph is exactly what you think. If you're moving in, let's say, that unit vector direction, then you look at the corresponding cross section, and you take the slope of the tangent line in that direction. Okay. Let's talk about the what you just asked about. What's the deal with the ds? So as you're moving in a given direction, as you move in that direction, you'll move in the input by some distance. We're going to use s to represent distance in whatever direction we're talking about. So ds represents how far do I move in that direction. ds dt, if you think about it, s being distance, ds dt just means how fast are you moving in that given direction. So keeping in mind that as a multiplicative factor, that multiplicative factor multiplies either by how far you've moved or how fast you're moving, right? And then the result tells you about the output values of the function. What linear estimate do we have of how much the function has changed, or what speed is the function changing? Right? So again, the multiplicative factor, it's what you multiply by light blue to get dark blue, and having set up these notations, having set up ds and ds dt to represent, distance and speed in the input, and df and df dt to represent distance and speed in the output. This factor, what you multiply by the one to get the other, in both of these equations, it makes really good sense to call them df ds. And then the familiar cancellation that we all sort of learned in single variable calculus actually works and is fine and therefore satisfying. So heads up, this is another common notation for a directional derivative, and this is going to have to be where we'll draw the line, and we'll pick up here next time. But let me just sort of put everything onto the screen now all at once, all together. Given a unit vector, this thing called the directional derivative, denoted like so, equals both of these expressions, can be interpreted as the slope of the graph, can be interpreted as a multiplicative factor, and can be thought of as df ds. All of these things are interpretations of the directional derivative. And what we'll see next time is how to use the fact that all of these things are the same to solve certain problems. Okay, good place to draw the line. Don't forget we have an exam on Friday. Don't forget, furthermore, none of this stuff that we did today is fair game for that exam, right? And so good luck to everybody. See you on Friday.